So thanks to be here. So as Thomas introduced me, I'm Yann Leseigneur. I'm working here as a postdoc. And I will talk about during this presentation about the Martian dust storms and more precisely on the different type of dust storm to different length scales and different methods to detect these dust storms. So as que je vais juste... So as a big picture of Mars and much more about the dust on Mars. So here, as you can see, maybe much more easy in the zoom because here there is much more sun. So this is a global map of the Martian surface, and the dust is almost everywhere on the Martian surface. As you can see here, this dust gives this orangish ochre color of to the Martian surface. And this dust is composed of mineral micrometer-size particles. These particles are oxidized, as you can see on this global map of the Martian surface. The orange part of the surface is where the dust is thick on the surface. And this dust is also bright, as you can see on this albedo map of the surface. There is a good correlation between the orange, so the very, very oxidized surface and the brighter surface. So as a summary, the Martian dust is mineral particles, micrometer size, oxidized and bright. Then we have different kind of processes that can lift dust from the surface injected into the atmosphere, mostly driven by winds. The first one is the direct injection of the dust particles, as you can see here on this scheme. So the winds just lift directly the dust and inject it into the atmosphere, and this process is not efficient on the Martian surface because the pressure is very low, and the main process is by indirect injection, and we call it saltation. So it's very easy to lift sand particles, so bigger particles like millimeter-sized particles. And then when these sand particles go back to the surface, it will communicate a part of its kinetic energy to other particles, dust particles, and then we have the injection of dust as an indirect process. And a third lifting process is by dust devils. So the dust devils, as you can see on this, it's a kind of convective vortices that take the dust from the surface and inject it at the top of this small dust tornado. So another lifting process. So now we know that we have dust on the surface, and we know a little bit how to inject it into the atmosphere. So now let's look at the atmosphere of Mars, so a dusty atmosphere. And for this part, I wanted to cite a French astronomer who worked in the Observatoire de Meudon in Paris. And he wrote a book in the beginning of the 20th centuries about all the works and all the observations since the 17th century. And he say about the dust clouds and the atmospheric dust. So here in French, and I will in English. So l'idée de la couleur de Mars fut suggérée d'abord par le français Honoré 1809. Elle fut ensuite énoncée en tout un observatoire à Angers, et enfin par Douglas qui mentionnait des poussières jaunes en 1899 par l'observation directe sur les continents martiens, voilà la figure 9 qui est juste à droite, ayant trouvé que ces voiles jaunes ou roux, moins transparents mais moins rouges que les continents, sont très fréquents Eugène Antoniadi say that the first astronomer that observed some kinds of yellow clouds on Mars is the French astronomer Honoré Flaugergue at the beginning of the 19th century. And then confirmed by different astronomers, and finally by Eugène Antoniadi at the beginning of the 20th century. And he also said that these yellow clouds are much more frequent than the white clouds. So now if we look at recent observations of Mars and the atmosphere of Mars, we can indeed see some white clouds and yellow clouds. The white clouds are the ice clouds and the yellow clouds, the storms. Eugène Antoniadi also say that qu'il a fait ressortir en outre que les voiles jaunes, on les aperçoit plus souvent vers le périhélie. So these atmospheric dust are mostly observed near the perihelion. So he suggests that there is an annual dust cycle that can be observed on Mars. So now if we look at recent data about the atmospheric dust amount, so here of diagram in the Martian atmosphere community. So this is the distribution of the atmospheric dust quantity. In the y-axis is the geographical latitudes, and on the x-axis it's the solar longitudes. So the solar longitudes is the way that we measure time during one Martian year on Mars. So it's defined as an angle between 0 degrees and 360 degrees. And we define the different season from a reference point, which is the 0 degrees of the solar longitude, which corresponds to the southern autumn equinox. And we can define all the season on Mars using this solar longitude, as you can see here, and we have the perihelion here next to LCBS 260 degrees and the aphelion at the opposite side. So if we look at, go back to this graph of the atmospheric dust amount, we indeed notice a first season, what we call the dust storm season, when we have the most of the atmospheric dust amount, as Eugène Antoniadi says in this quote here. And we have, at the beginning of the Martian year, a much more clear atmosphere season. So indeed, we have a strong annual dust cycle on Mars, as we can have here on Earth for the water cycle. So now let's talk about dust storms. So we have different kind of dust storms in different length scales. The most studied one are the regional dust storms, so with a major axis about larger than 2,000 kilometers. They have been observed many times. Like I think now we have much more 10,000 of detections of these regional dust storms. So in using UV visible imagery, thermal infrared spectrometer, and some observations in near infrared spectrometer. Then we have some results about these regional dust storms with statistical studies. We can study their spatial and time distribution, their horizontal extension, so their sizes, and also their trajectory, as you can see on this figure, which represent the different channels used by some kind of specific regional dust storms called flushing dust storms, because most of these dust storms form in one hemisphere and flush toward the equator to reach the opposite hemisphere using some channels, as you can see here, the 3 main channels to go from the northern hemisphere to the southern one. There is also some smaller dust storms called the local dust storms, and these dust storms are the less studied one because they are quite small, and we need some high spatial resolution instruments to observe them. So we have few images in visible imagery and also in near infrared spectrometer, and I will explain you some method to detect them in later in this presentation. So we have at the opposite length scale, we have also some global dust storms. Dust storms at the planetary scale. These dust storms are observed with all the instruments because it's occur on the overall planet, but they are the most unpredictable one. The three last one occur in 2001, 2007, and in 2018. And this is the biggest mystery, I think, for the atmospheric part of the Martian study, is why we have this kind of global dust storms. So here we have all these dust storms, and I will focus much more in local dust storms and global dust storms in this presentation. So some motivations why studying dust storms. Because the dust is a key parameter for the Martian atmosphere that notably alter the heat balance, and this dust is highly mobile and have a strong capacity to form dust storms, as we will see. So it's really important to also for the climate model to really understand this dust and the dust storms. So here are some actual questions about these dust storms. What are precisely the storm formation mechanisms, and also how we can form it, and how the dust storms grows from local scale to regional scale, and how they can reach the planetary scale on the global dust storms. That lead to the second question: what is the link between all these length scales? And the biggest questions is, why do we have these planetary dust storms, and how can we predict them? Okay, so last part of the introductions is how we detect the dust storms. This first one is by using some thermo-infrared spectrometers, so like tests on MGS and MCS on MRO for the Martian people. So with this thermo-infrared spectrometer, we can have some quantitative study to compute the dust optical depth, so the total amount of dust in an atmospheric column. And these instruments are really good for the cover of Mars. We can cover all the Martian atmosphere in one Martian day, but they have a very low spatial resolutions that with this data, we can only study the regional dust storms. A similar instruments with a similar spatial resolution is the UV visible large field imagers like MOC on MGS and Martian on MRO. So it's only images. We can only detect the dust storms. So with a qualitative study, and again with a really good spatial coverage, and but with a very low spatial resolution. So these two type of instruments are the mostly used to study the dust storms. So now we have a very big lack of information about the atmospheric dust and dust storms at a shorter length scales. So for the local dust storms. So during my thesis, and now I really want to focus on different methods to detect and to study the local dust storms. So two kind of instruments that can be useful to study them. The first one are the near-infrared imaging spectrometers, so mostly built for study the decomposition of the surface, so with a very high spatial resolution, then that will allows us to detect the local dust storms. And we can, as we will see in the following slides, we can have some qualitative study by computing the dust optical depth. So again, the amount of dust in the atmosphere, but we have not really good coverage of Mars. We can map the overall planet in one Martian year, but we have this high spatial resolution. And also we have the UV visible high resolution imagers, again built for studying the surface. So we can have a qualitative study, and again with a bad coverage of Mars, but with a very high resolution. So it will be very useful. So we start by talking about the near-infrared spectrometers and much more about the Omega 1. So Omega is the Observatoire pour la minéralogie, l'eau, les glaces, l'activité, pardon, qui est, je vais repasser en anglais, ça sera mieux, on board Mars Express in operation since 2004, so higher than 20 years of operations. And during my thesis, I used this data. So Omega is a visible linear-infrared spectrometer, and I have focusing my work on the infrared channel. So here you have the wavelengths of this channel, and this channel was operating between 2004 to 2010, so during more than 3 Martian years. And this instrument is an imaging spectrometer. So we can build some hyperspectral images, as you can see here, where each pixel of the image is a spectrum. So it's kind of one of the first times that we use this kind of instrument to study and to compute some quantity of atmospheric dust. So I developed a new method to do this automatically. So the principle of this method is here summarized in this scheme. So we start by taking one state of the atmosphere, as you can see here, an atmosphere with very low atmospheric dust amounts. So the sun's ray travels through the atmosphere, mainly composed of CO2 gas, like 95% of the atmosphere is composed of CO2 gas. And I reflected on this surface toward the instruments. So the optical path in the CO2 is very strong, that produces this very strong CO2 absorption band at 2 micron. And now if we take another state of the atmosphere, which is here with many dust in the atmosphere, the sun's rays are diffused on the atmospheric dust, and then the CO2 optical path is shorter, so we have this shorter absorption band. So by monitoring this decrease of the 2 micron CO2 absorption band, we are able to detect the atmospheric dust. Then I use also some grand measurements from Mars exploration rovers, which measure dust optical depths at 2 different sites on the Martian surface. And then I made a calibration to finally compute the dust optical depths in near-infrared wavelengths for each pixel of the almost 10,000 of Omega observations. So here, for example, it's 1 Omega observations with the dust optical depth retrieval that I've made, and I can combine them to produce some seasonal global maps. For example, here, during 60 degrees of solar longitude, and I can make it for almost all of the 3 Martian years of operation of the near-infrared channel of Omega. And here we'll focus on one part of this seasonal global map. It's a seasonal global map that corresponds to the global dust storm that occurred in 2007 during the Martian year 28. So as I said during the introduction, these kind of dust storms are very unpredictable, something like that. So actually, we do not have particular precursory signs for this kind of dust storms, but I wanted to know if with this new dataset, do we have some precursory signs? So here I computed the dust optical depth average during the clear atmosphere season. So at the beginning of the Martian year, where we have less dust amount, and we can see the variation during the different Martian year, and we can notice that during the 2 Martian years, so Martian year 27 and 28, before the onset of the global dust storm, we have this kind of high level of dust optical depths. And then we have the decrease of these dust optical depth the following years. So maybe it could be a precursory signs of the global dust storms, but the uncertainties are very high, so it's hard to conclude about this, but it can give the ideas of kind of precursory signs. Okay, so I also wanted to reconstruct this kind of diagram that I presented during the introductions, the latitude versus solar longitude, to compare it to the thermal infrared measurements, as we can see here. And by comparing these two kinds of measurements in near infrared and in thermal infrared, we can evaluate and estimate the dust particle size. And again, we can study different variations of this average particle size. Here for the again the global dust storms of 2007. Here it's the variation during in time as a function of the solar longitude, and we can see a large increase of the average particle size after the global dust storms onset. And we can also trying to understand how the dust particles are diffused after the global dust storm onset, here with this variation as a function of latitudes. And we can notice that the smallest particles are transported toward the southern pole, and then the biggest one are much more close to the global dust storm site onset. Okay, so now it was much more presentation about the atmospheric dust amounts, and now if we go back to our subject about dust storms, I have developed a method to detect the dust storms using this dust optical depth dataset that I have produced during my thesis. And this method is divided in two levels. The first one is by identifying all the omega observations. So in the datasets, about 10,000 of observations, to identify the observation that may contain storms. So selecting all the observations that have a large amount of atmospheric dust. And then the second level, so as an example here, we can extract some observations that have this large amount of atmospheric dust. And if we open the individual map, we have this different pattern of dust storms in the dust optical depth map. And if we look at the albedo map of the individual omega observations, we clearly see by eye the different dust clouds that are composed that compose the dust storms. But I wanted to make an automatic confirmation of all these dust storms, and not by opening manually all the omega observations and to confirm the detections. So I developed a method to confirm these detections by searching for observations before or after the storm, the observation storms. And for example, here I found observation 4 sols, so 4 Martian days before or 1 Martian year before, and we can see that the albedo map. On the albedo map, we have a clear decrease of the albedo before the dust storms, because we know that the dust is very bright. So when we have dust, we have an increase of albedo. So this method is based by searching the observation before or after and comparing the albedo values during these inside these clusters of high dust amount of the atmospheric dust. This second part, I'm currently working on it. So I will not present these results, but normally I will present this new and last results during the EPSC DPS on September at Helsinki. So if you are interested, you can go to see me at Helsinki. And here I will just show you some preliminary results about the first level of the method. So with this first level, we select almost 500 of omega observations that probably contain dust storms. And we can make some statistics with these observations. For example, here by studying the spatial distribution of these observations and potential detections. And we can see that we have many detections inside Elas planitia. So here, and also various linearies, which are regions, Martian regions we know to be source of dust storms. And also, what is really interesting is that we have the storm detections inside the on the flushing dust storm channels, as you can see here. And this will be very interesting to study these dust storms that move really, really rapidly. And then we have also detections near the southern polar cap, also another type of dust storm that are really interesting. Okay, so we can also study the time distribution of these dust storms. Here, the histogram as a function of a season on Mars. And we can notice that we have most of the detections of dust storms during the dust storm season. So this is normal. But we have some really high peak during the end of the southern spring, as you can see here inside the yellow rectangle. That is kind of surprising, because if we compare to the biggest Martian dust storm catalogs that have been produced using UV visible imagery, during the Martian 27, so for the left part of the graph on the left, this corresponds to the blue bar. On UV visible imagery, we do not have observations. So by discussing with colleagues that produced the imagery catalog, we call the some that have not been detected by the other catalog. So this is really promising, and I'm working actually on it. And these omega detections are also complementary, because during some parts of the Martian year with the UV visible imagery, they cannot take images. So we can have some inputs about the dust storm detections, for example, during the end of the Martian in 2029. So omega is kind of old data, but we have new inputs about the storm. So I think this is very nice. And one of the also positive points of omega and Mars Express, the orbiter, is that we can have some observations at different local time. That is not the case for most of the other instruments. So we can also study the diurnal variations of the detections. And we can notice that we have most of the detections between noon and 6 p.m. And like 3 or 4 years ago, another mission called EMM arrived in the Martian system and have an equatorial orbit that allows to have some different local time observations, like 10 Martian years after the arrival of Mars Express. And now we have few detections, like less than 100 detections at different local time. And we can notice that we have the same trends of the diurnal variations of the dust storm detections, again, between noon and 6 p.m. But also what is new with omega that is that we have some detections really early in the morning between 4 and 6 a.m. that has not been reported by the EMM mission. So also another thing, and I am working on it actually. And now to focus on one particular dust storms is again the global dust storms in 2007. We know that these dust storms may formed at the southern hemisphere at Noakis, near the solar longitude of 264 degrees. But we also have images that show one precursory storm that formed at Cruiser at the northern hemisphere 2 degrees of Celsius before. And we know that at Cruiser is also the formation site of the global dust storms, the last global dust storm in 2018. So it's really interesting because these cruisers that actually go towards the equator and stop close to the Noakis dust storms. So actually, we do not know if the cruiser dust storms initiate the Noakis dust storms. So it's really interesting to study this. And with Omega, we have 4 observations during LCBS 264 between Cruiser and Noakis sites. So we wanted to know what Omega can give us as an information. So here, this is the dust optical depth, so the atmospheric dust amount for the 4 Omega observations. And we see that we have a kind of connection in dust optical depths, high values of dust optical depths between these 2 regions. And if we look at closer to this latitudinal profile of dust optical depths, we can notice strong variations between these 2 regions. And we can separate this graph in 3 different clouds between Cruiser and Noakis. And this different clouds seems to be confirmed by other dust optical depth retrievals using, again, Omega, but at higher wavelengths. So now with the Omega inputs, this global dust storm seems to have formed directly in the southern hemisphere at Noakis and not in the northern hemisphere. So yeah, after more than 15 years after the onset of global dust storms, we still can give some new information about the formation of this global dust storm. Okay, so I've finished to talk about Omega, but I wanted to now go back in time and talking about the fourth kinds of instruments, the UV visible high resolution imagers like HRC or Mars Express. Just to say that I'm currently starting to work on it, notably with Seydou, who is here in the room as a Master 1 internship. And he will work to develop an automatic dust storm detection method and applying on HRC data to also start to have much more data about local dust storms, which is really important. So after talking about archive data, I wanted also to talk about future missions, and notably the Martian Moon's Exploration Mission, MMX, where here in LATMOS we are involved on this mission. So this is the JAXA mission, which will arrive in 2 years in 2027. And the Martian system, mostly to sample the Phobos surface, but also to study Mars and the dust and water cycles and their different interaction. And here in LATMOS, we are mostly involved in the MIRS instruments. So this is the near-infrared imaging spectrometer on board MMX. And here we have different informations about the MIRS instrument for the Mars observations part. So we will have a similar spatial resolution as Omega that allows us to study the local dust storms. And what's new is the temporal resolution of one specific observation mode that I will present you in the following slide. That allows us to have some observations with a very high temporal resolutions down to 15 minutes. So MMX, we will have an equatorial orbit that allows us to make many cool things. So we define 4 observation modes for MIRS. The first one is the nominal mode, so day-to-day mode. Then we have the global mode that allows us to make a speed global map of the Martian atmosphere. Then we have the limb mode that will allow us to hopefully to make some vertical profiles of dust and ices. And then we have the region of interest mode. This is for me the most interesting observation mode, which will allow us to have observations, so MIRS observations every 15 minutes for many hours, which will be the final product of MIRS. And with the actual version of this code, we are able only to have the aerosol contributions, so the dust contribution and the water ice contribution in the final version of the spectra, that is the output of the code. And we do not have gases. This is the current step that we wanted to implement in the code. But with this spectra, we wanted, and our goal is to prepare the aerosol retrieval pipeline. So aerosol for Mars is the combination of the dust, the atmospheric dust, and the ices, so CO2 ices and the water ice in the atmosphere. So we need to prepare the pipeline for the future observations, and to do this, the future retrievals, we compute what we call a lookup table. So this is a huge bank of spectra, as you can see here, with different parameters, and we will compare this lookup table to real MIRS observations, as you can see here. And by comparing them, we'll be able to retrieve different characteristics of the aerosols, for example, the dust optical depths and the ice optical depths, so the amounts of atmospheric dust and atmospheric ice. So this is a work in progress, and we'll have a poster again at EPSC. So if you are interested, you can come to see me. So as a summary, but this is not the last slide, but first summary of this presentation about the dust storms. Firstly, we have a strong statistics about regional dust storms, but not the local dust storms, and we do not really know how the dust storms grows from the local to regional dust storms. So I have presented you a method to compute the atmospheric dust quantity using near-infrared spectrometer with a high spatial resolution. And I'm currently working to the final version of the Omega dust storm catalog with much more focus about the local dust storms study to characterize these dust storms. We are also currently preparing the MIRS observation that will give many inputs about local dust storms, notably to trying to catch the formation and the evolution of dust storms at high temporal resolution and high spatial resolution. And we are starting to work on HCIC data to have some automatic local dust storms detections with Seidu in internship. So I wanted also to show some perspectives about Martian dust storm study, because currently we have less mission towards Mars, but we have many archive data that we can use. For example, the instrument on Mars Express, MRO, or also Viking missions at the end of the 70s, sorry, that can give us some important information about local dust storms and also some, for example, dust lifting processes and interannual variations of the dust storms detections. And these archive data are really important to prepare the future missions. So as I mentioned, MMX mission with MIRS, but also with different imagers on board the mission as Tengu or Orochi. And also there is different kind of mission proposal as Lightship 1 and Spotlight, which are missions proposed by ESA with meteorological payloads. So it will be very nice kind of missions for dust storms study with spectrometers, imagers, and also a LiDAR. And we are particularly interested by the LiDAR part in LATMOS. So with different two type of spacecraft with high equatorial orbit and low polar orbit, which are complementary for the meteorological study. And then there is also the MMATIS mission. So again, the LATMOS is involved in this mission proposal for the medium class ESA missions. So with one particular instrument, which is MAC, which is Aurora camera with a photodiode that will allow to compute the dust opacity of the atmosphere and then to detect dust storms. So with a kind of mission that is quite nice with two twin satellites with the same payload that can give some interesting inputs as a two angle of view around the planet. So this is my last slide. So if you have, thank you very much. If you have any questions.